everyone. Great to see so many of you at the TEP colloquium today. Before we get started with Misha's talk, let me briefly announce the TEP Small Grant Award winners of this year. If you haven't applied in the past, this is a regular program where students can get travel support to attend conferences. And this year's awardees are Eleanor Chang, Hayden Foote, Ian Messison, Dishan Chu, Polly Hyman, Vikram Manikantan, and Yang Sai. Congratulations all. I hope you bring back great insights from these conferences and maybe at some point then write papers about it that we discuss more in TEP. So congratulations again. And I will stop speaking. Our TEP colloquium speaker today is Mikhail Ivanov, currently visiting from IIS, where he's an Einstein Fellow. Misha got his PhD from EPFL in Lausanne, Switzerland, and then was a postdoc first at NYU and now at IIS, and moving to MIT as junior faculty in the fall. And he has really been one of the groups, part of one of the groups, teaching us how to use the information in the whole galaxy power spectrum, and now also higher order statistics, and concerning all kinds of physics with that. So I'm very excited for this talk. Please take it away.
Thank you very much, Elizabeth.
Yeah, do share your screen.
Yes. Yeah, thank you very much for this kind introduction. All right, I guess everything is working here. Thanks for having me here. It's a great pleasure.
Sorry,
Yeah.
there's a small window underneath.
Oh, okay. This, I guess. Better.
Yeah.
Okay. I work most of my time. I work on cosmology, and cosmology is to a large extent an observational science. And it actually started with a very simple observation more than 100 years ago. So why the sky is dark at night? Oh, you might say this should be very easy just because there is no sun. But in fact, it is not the answer to this question, because if we live in an infinite, eternal, static Einstein universe, then, Newtonian universe, right? Then and if we look at any point in the sky, like any hour line of sight, we would necessarily hit a star. So this means that in this universe, it's simple classical physics, the sky should be as bright as the sun or even brighter. And this paradox, known as Olbers' paradox, was one of the most crucial observations that motivated the modern cosmology. And of course, now we know the answer to this question. This is because we get to see a finite number of stars just because the universe has a finite age. So there's only a finite number of stars we can possibly see, and that's why the sky is dark. But since then, this was 100 years ago. Since then, basically, our method didn't change. Like our philosophy is more or less the same. We look at the sky and study various objects of the sky, things like galaxies, and then we do cosmological inference by, extract different kinds of information by looking at the distribution of various celestial objects. So this program of, looking at the sky and measuring various things and relating them to cosmology has been very successful. And now with galaxies and the CMB, we can trace the evolution of our universe over the time scale of more or less 14 billion years. And here I'm showing you the video from it's a compilation of various surveys, SDSS, BOSS, extended BOSS, and basically in this video, every single dot over here is a galaxy that we actually observed, whose redshift we measured. And you can see that we used galaxies as tracers to create three-dimensional map of our universe, and different colors here, they correspond to different tracers, different types of galaxies. And you see that using this method, we were able to reconstruct the history of our universe for at least 10 billion years. And we can go even further and observe things like the cosmic background radiation, which is depicted here as a surface of this sphere of our knowledge. So this program of extracting cosmological information from CMB galaxies has been extremely successful, and it gave us a very coherent picture of our universe. It all started with something like inflation, a primordial accelerated expansion. Yes, there is a question.
So this is about the animation you just showed.
Yep.
Is there a reason why it appears so asymmetric?
With respect to the origin, right? It has to do with the fact that most of the galaxies we observe from the Earth. So there is a galactic, plane that we cannot really eliminate. You see, this asymmetry is basically asymmetry in our, because we observe from within our solar system, from within our galaxy, and so on. We want to look for much higher reshifts. Yeah. All right. So we know that something created the structure, something set up the initial conditions, which most likely was inflation, primordial accelerated expansion of our universe, and then those fluctuations, they evolved later on as the universe was expanding and cooling down. And at some point, it cooled down to the point that the first atoms were created, and the radiation that was left over from that epoch, called as cosmic background radiation, basically gave us the very first image of our universe, the very first snapshot. And then these fluctuations, they continue to evolve, and we also observe exact same fluctuations in the form of galaxies at low redshifts. And galaxies are, similar to the CMB in the sense that they also provide us with a snapshot of our universe. But now we can measure their redshift, so we can actually, have this three-dimensional map of our universe. So basically, it's like having this equivalent to having many snapshots of our universe. And a huge success, theoretical success behind this observations is that we can describe all these, fluctuations with very few ingredients that are base ingredients of our standard model called lambda CDM, or inflationary lambda CDM, if you will. So basically, if you assume inflation, then full dark matter, then a cosmological constant to explain the late time accelerated expansion, then that's it. This is enough. This is going to be enough to explain all the observed data. But also know that this picture is at the very least incomplete. So first of all, there are no unknowns, so things that we know we don't know. For instance, we don't know what was inflation exactly, what was the mechanism that created the initial fluctuations. Also, we don't really know if dark matter is really cold. It might be that it's not entirely cold, or at least it's one of the fractions of dark matter is not cold. And on top of these known unknowns, also there are unknown unknowns. So things we don't know, right? Those are surprises, some new discoveries that come from the data, and sometimes we're not prepared, and we don't have any theoretical explanation for them. And in my talk, I'm actually going to present you one of the examples that we have recently made. So an example of unknown, which has to do with the apparent detection of parity asymmetry in the initial conditions. All right, so the working horse of cosmology for many years has been the cosmic microwave background, or specifically its fluctuations. So the CMB temperature fluctuates on the sky, and these fluctuations, they represent a Gaussian random field. So all its statistical properties are encapsulated in the two-point correlation function called the power spectrum. And here you can see the CMB fluctuations power spectrum, the temperature power spectrum. And it has a very complicated shape. So it has a plateau on large angular scales. It has some oscillations on intermediate angular scales and an exponential damping at small scales. And this, this shape is very complicated. But with lambda CDM, we can fit it with only 6 parameters. And this is precisely how we measure them. And in particular, we measure the densities of dark matter, baryons, and dark energy. And let me show you the movie, how we do so. So we just, calculate how does the CMB power spectrum respond to variation of, well, in this case, density of dark matter. And you can see that, it changes quite drastically. And this is precisely how we obtain this number that, 26.8% of our universe is made of dark matter, just by observations of this, by comparing our theoretical predictions with the data. Now, with large-scale structure, we would like to do something very similar, because large-scale structure also looks a lot like the CMB. So galaxies that we observe, they represent fluctuations of the density field. So we can write down, we can introduce the overdensity field delta rho over rho, where rho is the background density and delta rho is the density fluctuation with respect to the mean. And as I said, galaxies, they basically they cover certain volumes, so they give you three-dimensional information. So in this case, we can characterize them by computing different observables like the power spectrum now as a function of three-dimensional momenta three-dimensional momenta k, or the wavelength lambda. And here on the right, I'm showing you how the galaxy power spectrum looks like as a function of scales, or here as a function of wave number. And here I'd like to maybe point out that these observations of galaxies and trying to extract cosmology from the shape of the galaxy power spectrum used to be the main source of cosmological information back then. So in this plot, I'm showing you the let's say the amount of information as well counted as a number of available modes as a function of time. And you can see different data points that correspond to various surveys. Most of them are so those are galaxy surveys, and we know that, for instance, in the 80s and the 90s, there were only galaxy surveys. There were no CMB surveys back then, and this, the log of information was growing with time, and it keeps growing right now. And I'd like to stress here that we extract a lot of information from the CMB, but also the amount of this CMB information is limited. It's fundamentally limited, and we have almost reached the limits. And here I'm showing you the amount of information in the CMB, and you can see that we have some surveys ongoing right now, such as DESI, that will give us equal amount of information as the CMB. And in the future, with future surveys like MegaMapper, we're going to get much more information. So in theory, large-scale structure is more powerful than the CMB. So we can imagine, improving our understanding of cosmology by orders of magnitude from these surveys. And this is the main motivation for the full shape analysis that I'm pushing, that I'm advocating for. So basically, let's extract cosmology in exactly the same way as we used to do it with the CMB. So let's measure different correlation functions of the galaxy distribution and try to fit them, extract cosmology directly from the shape of the galaxy power spectrum. And this is a great idea, just because CMB large structure, they probe different scales, different redshifts, and also different physics. And in particular, large scale structure gives you a direct probe of dark matter fluctuations, which is not the case for the CMB. So CMB is not really sensitive to the fluctuations of dark matter. And yeah, as I mentioned, large scale structure principle covers three-dimensional volume, and just naively, by mode counting, contains orders of magnitude more information than the CMB that would like to convert into orders of magnitude better cosmological parameters. However, this program turned out to be, so people had tried to execute this program back then in the 80s, but it didn't quite work because of nonlinearities. So the big issue here is that, and a big difference between CMB and large-scale structure is that CMB is a truly Gaussian or nearly Gaussian field, whereas the galaxy density is not. And in particular, if we take a look, so here I'm showing you some snapshot from a galaxy formation simulation, and you can see that on large scales, really the distribution of galaxies looks a lot like a CMB. So you see some random patterns of overdensities and underdensities. But as you start zooming in, you will start finding more complicated nonlinear structures, such as filaments, such as clusters of galaxies and individual galaxies. And of course, linear theory cannot be used to describe those objects. And this picture, the breakdown of linear theory is illustrated here, is illustrated well on this plot. But basically here I'm plotting the galaxy power spectrum data versus the linear theory prediction. And you see that on large scales, they agree. So we know that on large scales, the distribution of galaxies looks quite Gaussian and hence linear. But as we go to smaller scales, so higher wave numbers, we're going to see some difference. So linear theory is not going to be enough, and we'll see this disagreement between linear theory and the data. So let me say a few words about sources of nonlinearity. So the very first source of nonlinearity is the nonlinear clustering of dark matter itself. So you can think of this as some kind of Jeans instability. Then the second source of nonlinearity is the galaxy dark matter connection, which is illustrated in this snapshot from another galaxy formation simulation. So basically, here the gray structure, these gray structures correspond to fluctuations of dark matter, and the yellow structure, they basically those are simulated galaxies. And you can see that on large scales, more or less, they trace each other. So where you see, if you see some overdensity of dark matter, it also corresponds to overdensity of galaxies. But this relationship is not exact. And for instance, in this void, you see that there is some dark matter structure, but there are almost no galaxies. So this relationship between the two is not linear. So it's linear on large scales. And in principle, this is how we try to describe it. So on large scales, you would say that density of galaxies is linear proportion to density of dark matter. But then you need to take into account some corrections to this relationship. And on large scales, you can write delta square. So delta is a small number here. So delta square is still kind of smallish. And then you can go on and write down more complicated dependencies, like you can write down the operator field from the tidal field and so on and so forth. So this is how we describe the galaxy dark matter connection on large scales. And there are other effects that are conceptually similar to galaxy dark matter connection, also known as galaxy bias. So those effects are, the baryonic feedback and redshift space distortions, which physically are somewhat different, but conceptually we can also take them into account by some kind of Taylor expansion similar to the one that I wrote here. And at this point, it's important to stress that this relationship involves some unknown parameters that we call bias parameters, which are actually some nuisance parameters. So we have to marginalize over those parameters in any realistic data analysis. So because those parameters basically they capture our ignorance about the galaxy formation processes. And so given all these sources of nonlinearities, these effects were important even in the era of very first galaxy surveys. For instance, here I'm showing you the power spectrum from the SDSS survey from the beginning of precision galaxy clustering science, 2006. So you can see that, well, here you see the data and also the prediction of linear theory. So basically, this is an analog of the plot that I just showed you. And on large scales, linear theory is kind of fine, but then on small scales, there is an offset between the two. And basically this problem, so there is a problem that the theoretical error that is, well, encapsulated here by this difference was much more important, was greater than the statistical errors, even at the beginning of galaxy surveys, in the era of very first galaxy surveys. And basically the standard approach until recently was to kind of ignore or, to a large extent, don't think too much about this theoretical error, but try to focus on observables that are approximately stable with respect to nonlinear effects, such as the distance and the growth information. And basically, in this way, you're going to discard all of shape information, all the cosmology dependence that is encoded in these data points. And the original motivation for my research was to do better and to actually use this extra information to learn something new about cosmology. But for that, we have to understand these nonlinearities. And basically, there are two ways to do that. So you can use either analytics or numerics, so which is to say n-body simulations. So let me discuss these two ways in more detail. So on the one hand, simulation, you can run simulations. The simplest one being the n-body simulation, which seems to be a good thing to do for matter clustering, because for matter, this is the full, in principle, this is the full solution. This is the exact calculation, which is valid for any scale, for any range of scales. But however, the problems appear when you try to describe galaxies, because there is no fundamental first principle model for galaxies. And so there's been a lot of progress in this field, but I think that still there is some disagreement, and it's not clear how to describe galaxies systematically. And also running the simulations is still time consuming, so this approach is not very flexible in general. And ideally would want to have something like MCMC analysis, so we're able to compute the galaxy formation observables in, let's say, 1 second, and right now it's not possible with simulations. An alternative to this is analytics, and basically doing calculations in terms of perturbation theory. So this, of course, perturbation theory breaks down at a certain scale, so it's fundamentally limited in terms of distances, in terms of range of scales. But however, perturbation theory gives very high accuracy and precision on the range of scales where it is applicable to. And in principle, it's a very fast and cheap way to calculate observables, and which means that it's very flexible, and you can easily go beyond lambda CDM and explore different new physics scenarios in this framework. And also, it's a very natural framework to marginalize over all these astrophysical uncertainties, where basically, all these astrophysical effects are parameterized by a set of nuisance parameters, and we just marginalize over them. So this has certain advantages over the simulation-based approach. And in most of my talk, I'm going to focus on this perturbative techniques. So why do formulas work at all? Because you might think that, look, galaxies are, is a complete mess. The physics is extremely complicated. Why do we believe that formulas would work at all? So here, I would like to bring an example of fluids, let's say water. So we also know that water is very complicated, and the dynamics of single HO2 molecules, these dynamics are very complicated. You need to take into account many intermolecular forces. But however, we also know that if we go to large scales, we can introduce some coarse-grained fields like the velocity field, the pressure field, density, and basically we can write down something like the Navier-Stokes equation, which for the incompressible fluid takes this form over here. And we also know that the Navier-Stokes equation should be valid for any kind of fluid, for any kind of collection of particles. And typically we just write down this shear viscosity operator. But in principle, why do we stop here? In principle, we can also write down, higher derivative terms. We can write down something like the fourth order gradient acting on the velocity field. And these terms should be there, but we normally ignore them just because they're subleading in the gradient expansion. So we can estimate the size of these terms, and we're going to find out that they are suppressed as long as the distances we're looking at are much greater than the mean free path of the fluid molecules. So we have a manifestly convergent gradient expansion, and we can, even though the small scale microscopic dynamics is very complicated, on large scales, everything simplifies, and we can just do fluid, and in principle, we can get any precision that we want. We can include all these operators, no problem. And we can have this nice analytic description thanks to the separation of scales. And actually, this is the definition of a fluid is the collection of particles on scales greater than its mean free path. So now we can apply the same logic to galaxies, because the galaxies also happen to enjoy a separation of scales. On the one hand, we have the scale of the, let's say, the virial radius of halos, so the scale, the halo size of order a few megaparsecs. So this is the scale that controls all this complicated physics and astrophysics that has to do with halo formation, galaxy formation, baryonic feedback, and so forth. But on scales larger than that, the distribution of galaxies behaves like an effective fluid, same way as water behaves as fluid. And it's crucial that this fluid is non-relativistic. So the relativistic effects become important only when we reach the scale of the horizon, which is few gigaparsecs. So basically, the idea to describe galaxies as an effective fluid is called the effective field theory of large-scale structure. It has been put forward more than 10 years ago, and since then, there were many people working in this field. And I myself created a framework called time-slice perturbation theory, which basically allows you to calculate, different large-scale structure observables in terms of Feynman diagrams. So this is technically speaking, path integral formulation of the FTF-Large structure that allows me eventually to get to 1% and sub% understanding of galaxy formation observables. And we have put these calculations together in a code called class PT. And now, with this EFT, we can describe the galaxy power spectrum quite well. And these calculations are publicly available. You can check out my GitHub webpage. And now basically it's clear how to proceed and how to take into account this, higher order corrections, subleading terms, to compute things like two-loop, three-loop corrections, and so on and so forth, and also how to include this non-Gaussian information, how to compute a 3-point function, 4-point function. The only caveat here is that these calculations, yes, please.
Yeah, sorry, I'm not an expert in this, but you've gone from something which is fluid mechanics and have made a sudden jog into quantum field theory.
Right.
And I don't know what you mean when you're talking about Feynman diagrams or loops in this context.
Yeah, here, so here, our loops basically they capture a perturbative expansion. So for any perturbative expansion of a statistical system with ensemble average, you can reproduce perturbative calculations with Feynman diagrams. So this system is purely classical, right? So there are no quantum effects here. But the methods of quantum field theory, they also apply to classical systems like path
You have an
integrals.
analogy to define structure content, which allows you to get something which is convergent.
Well, yes, here is going to be really the distance expansion. So effectively, so this is an effective. It's more similar to, let's say, chiral perturbation theory, where you have explicit distance and control energy expansion. So, but in principle, yes, we have a set of small numbers here that are, well, here the gradients of the fields that allow us to, get this conversion expansion. Thank you. That's a very good point. All right. Introduce this pipeline, and basically at this point you might ask whether I would show that this whole approach is correct, and I think that there are two answers here. So from the mathematical point of view, that's the only option, so it must be correct. But also we have some explicit checks. We have participated in blind data challenges, and also have tested this effective field theory at the field level, not at the level of the actual galaxy observables, but at the level of, let's say, the maps, the galaxy distribution. So we can also calculate the entire galaxy distribution here. So let me describe maybe these tests in detail. So when we participated in the challenge, the idea was that so we were given the data that basically mimicked the actual data on the galaxy distribution, but the total volume of this data was 100 times greater than the volume, let's say, of the universe. So we had, the same data, but with very small error bars, basically 0.1%. So here you can see that, the errors are so small, you cannot really see them on this plot. And this is our error bar, which is much smaller than 1%. And the idea was to extract the true cosmological parameters from those simulations. And we have passed this test with this, high precision requirements. And the second test we did was to really calculate the entire galaxy distribution, which we call the field level comparison. And basically you can see that on large scales, or you can see it's called the bias model. On large scales, the maps, the actual map of the, let's say, simulation that mimics the galaxy survey, what the galaxy survey sees. Basically, they're very similar, maybe unless you go to very small scales where you see some difference. But we also know that this difference must appear because our gradient expansion will break down. So this gave us confidence that this should work, and we apply this to data from the BOSS galaxy survey. We extracted things like the galaxy power spectrum, the bispectrum, so the 3-point function. So as I showed you before, the non-Gaussianity is a specific, very important property of the galaxy distribution. Any optimal analysis should include this non-Gaussian observables, such as the 3-point function. You can see it over here. And we're able to obtain measurements of cosmological parameters similar to the ones coming from Planck CMB data. So here, the blue posteriors result from our analysis, and the red posteriors, they represent contours from Planck, which is the benchmark in the field. And I guess at this point, there are two comments that I can make. First is that the size of the error bars is more or less similar. So it was kind of surprising that, for instance, we can measure H naught with almost the same precision as Planck. And the second statement is that these contours, they overlap quite significantly, so we don't see any strong tension, well, there is a little bit of tension here around sigma that I'm going to comment on later. So, but other than that, we see that this, the Gauss distribution is very consistent with the distribution of the CMB fluctuations. And a small comment on these tensions, that these measurements, they contribute significantly to our understanding of measurements of the Hubble constant, and also of the growth of dark matter fluctuations captured by the parameter S8, whose formal definition is given here. Well, sigma 8 is the mass fluctuation amplitude in the spherical, in the spheres whose size is 8 megaparsecs. Well, it's some historic parameter, but basically this is the amplitude of the galaxy power spectrum at low resolutions. And you see that there is some difference between the direct and indirect measurements of these quantities. And I think that the hope of many people is that those tensions may indicate actual incompleteness of our vanilla lambda CDM model. But I think that, people tried very hard to resolve this Hubble tension. I think that it will be fair to say that there is no compelling theoretical explanation yet. In terms of the growth of clustering, I think the problem is very different. So we have many measurements, some of them independent, like measurements coming from this spectroscopic galaxy clustering, photometric galaxy clustering from surveys like DS, and those disagree at the 2 or 3 sigma level with the measurements coming from the CMB, which are indirect. So CMB predicts the latent clustering that we can directly confront with the actual data, and we find this 2 sigma tension. Well, in this case, in the case of the so-called S8 tension, the problem is that there are too many explanations, and we're not able to distinguish at the moment between them. Whereas the problem with the H naught tension is that there is no compelling theoretical explanation yet. But hopefully, with more theoretical work and with better measurements, we'll be able to understand if these tensions, they have any implications as to whether lambda CDM is incomplete. Yes.
Do you know why the EBOS quasar measurement was S8 measurement was so high? Do you have a?
Well, if we exclude, let's say the systematics observation, I'm not sure. I would say that
Do you know specifically?
it just happened to be high.
Yeah. You know what observation systematics about quasar specifically that might play your role here?
Yes, it's called catastrophic redshift failures.
Okay.
Okay. So we can discuss this. Yeah. All right. So let me now
Another question in the back.
Yes.
I have a question about your formulation for applying the perturbations. So does it only work for small perturbations, or does it also work for large perturbations at the scales of galaxy clusters and so on?
You mean this effective field theory techniques? They only work for small perturbations, only for small. So here, yeah, that's a good point. We only focus on this quasi-linear regime. And for large perturbations, these perturbative techniques absolutely don't work. It's complete rubbish. So we should use simulations instead. All right. So let me now say a few words about one of the advantages of the perturbative techniques, that we can easily explore some non-standard scenarios with them. So they're very flexible. We can modify, we can explore these other cosmological models. And in the past, we have studied many of these scenarios, including the ones that are relevant for the Hubble tension in the context of the so-called early dark energy model, and also, things like dynamical dark energy. But in this talk, let me focus on 2 other extensions, and on 2 particular, examples where this galaxy power spectrum measurements, galaxy full shape measurements will give you a lot of interesting information. So this is inflation. One instance is inflation, primordial non-Gaussianity. And the second instance is the nature of dark matter. So in the remainder of my talk, I'm going to discuss these two particular examples. So let me say a few words about inflation. So inflation, the cartoon picture of inflation is here on the left. So basically, inflation is a primordial acceleration expansion, where our universe, during which our universe looked like a balloon that was, inflated by a field called the inflaton, and this field was slowly rolling down its potential. So this rolling was so slow, so the energy density was nearly constant, and hence the accelerated expansion, similar to the cosmological constant. And during this time, the little ripples on the surface of this balloon that here represent the fluctuations of the metric field. Well, here the scalar curvature fluctuation, but in principle there could also be gravitational waves. So basically, those little fluctuations were stretched to very large sizes, and they later became the seeds for the structure formation later on. And inflation, the single field vanilla slow roll inflation, is characterized by small parameters that capture the small velocity, small acceleration of the inflaton and its potential. So these slow roll parameters are called epsilon and eta, and the key observables, such as the let's say relative amplitude of tensor modes with respect to scalar modes, and also the amplitude and the tilt of the primordial power spectrum of primordial fluctuations. So those are parameterized by the slow roll parameters. So the tilt is given by this expression, and the tensor to scalar ratio is given by this expression. And those were the key observables that we were looking at in the past in the context of the CMB. And here you can see the state-of-the-art constraints basically on these two numbers, the power spectrum tilt and the tensor to scalar ratio. We detected the tilt. We have not yet detected the tensor modes, the primordial gravitational waves. So this is the state of the art of our understanding of the vanilla single field inflation. But this has left many questions to be answered. And the most pressing one is, what is the energy scale of inflation? So for this, we really need to measure this quantity, the tensor to scalar ratio, the amount of primordial gravitational waves. But then there are other questions, such as how many degrees of freedom there were during inflation, how fast did they propagate, and were there any interactions during inflation? And we can answer those questions with large K structure. So we cannot really answer the first question. So that's why I'm going to ignore it in the rest of my talk. But the three other questions I'm going to discuss in detail. So let me say a few words about primordial non-Gaussianity. So the biggest success of inflation, in my opinion, is that it predicted very naturally the Gaussian spectrum of primordial fluctuations, which matches what we see on the skies, matches the CMB observations. But we also know that there must be some nonlinearities, because there were some interactions produced on Gaussianity, and there must be interactions at the very least due to gravity, because we know that gravity is nonlinear, couples things. So there should be some primordial non-Gaussianity because of that. And this non-Gaussianity we characterize in terms of the skewness of the distribution of primordial fluctuations. And this skewness in turn is parameterized by the parameter called FNL, which is basically, so the relative skewness equals 10 to minus 5, the amplitude of primordial fluctuations times FNL. And here on this plot, I'm showing you the effect of this FNL, or here I had to crank it up by basically 5 orders of magnitude to make it visible. But in principle, we're interested in the regime where FNL is order 1. So we're looking for an effect which is extremely small. I'm going to show you that even though it's very small, we're still able to measure it. So let me say a few words about different physics that generates non-Gaussianity. So the simplest type of non-Gaussianity is called local, and it's produced in scenarios like multi-field inflation or modulated reheating, where basically you can assume that your inflaton field decays into, let's say, standard model particles, and its decay rate is controlled by another field, sigma in this example. And then you can calculate the initial conditions that are generated in this model, the scalar curvature field zeta, and it's going to be given by sum of the Gaussian contribution plus the Gaussian contribution squared with a parameter FNL local in front of it. And this is precisely the parameter that determines the skewness or the bispectrum. And the theoretical target that comes from various multi-field models is that FNL should be within the range from 1 to 10. This is the interesting target for us. And there is also an interesting statement that is called the consistency condition. It's basically a theorem that was derived by Maldacena, is that the detection of any local FNL, detection of FNL local not being 0, will automatically rule out single field inflations. So basically, in the single field model, this type of non-Gaussianity is forbidden by the symmetries of the problem. And that's why we are very excited about this particular, observable, because this is a very clear test of, how many fields there were during inflation. Now, what about the single field inflation? I mentioned that inflation was actually single field. So what could we measure in this case? So according to Maldacena, in vanilla single field, really nothing. So we can calculate the, let's say, the quadratic Lagrangian for our inflaton field, and the correction. So it's going to be, the action is going to be quadratic, and correction are going to be suppressed by the slow roll parameters, absolutely undetectable. They're too small, but in principle, there is nothing wrong in having, so in this Lagrangian, having cubic terms, cubic interactions, and more complicated, let's say, fourth order interactions. They don't violate any symmetries, and in principle, they could be there in some explicit models of single field inflation. And this observation gave rise to a, field that was called the effective field theory of inflation. So it's a program of parameterizing all possible Lagrangians, of writing down all possible Lagrangians consistent with symmetries. And if you follow this program, you're going to find that there are only two operators. So there are only two types of, cubic interactions, cubic terms here that generate non-Gaussianity. And you can also introduce, the similar FNL parameter for them, their amplitude. So these two particular, let's say, operators, they correspond to types of non-Gaussianities called equilateral and orthogonal, as opposed to local. Altogether, they're called non-local. So the typical theoretical target for FNL non-local is, in the range from 1 to 100. And these different scenarios, they have been constrained by Planck, by the cosmic array background observations, and we obtained the following results. So we didn't detect anything yet, but also with the SIMBI data, we're not able to cover the full interesting parameter space. So there is still a significant chunk of parameter space that is left unexplored with the SIMBI. And the problem is that these constraints cannot really improve by more than, let's say, factor of 2 with future SIMBI measurements. So this is precisely the limitation by the cosmic array background observations that we're going to resolve with galaxies. So with galaxies, so our data right now is not as good as Planck, but we're able, even with the current data, we're able to obtain direct constraints on these parameters, on these inflationary models. So with Oliver Filkos, who is here in the audience, and also Giovanni Cabas, we're able to obtain first constraints on primordial non-Gaussianity from galaxy surveys, including the ones coming from the single field type of non-Gaussianity. So our constraints on these FNL parameters right now are a factor of, let's say, 6 worse than the ones from Planck. But for us, this is only a proof of principle that such a measurement, even though it's very intricate, it's a very small effect, but still can be done at the level of galaxy surveys. Even in in the presence of all these complicated nonlinearities, we're able to obtain these constraints and basically resolve all these issues that were problematic or thought to be problematic before. And you can convert these constraints for the equilateral type of non-Gaussianity. You can convert this constraint into the constraint on the sound speed of the inflaton, because the relationship between the two is completely fixed by symmetries. And basically, we have obtained that the speed of sound of the inflaton during inflation should be greater than 1% of the speed of light. All right, and in the future, these constraints are going to improve dramatically. So with future surveys such as DESI, Euclid, and Spherix, we're going to obtain a limit on or measurement of FNL local with error bar 0.5, and with in the context of single field inflation, we're going to obtain error bars at the level of sigma FNL non-local 10. So, which means that by this time, with these future surveys, we'll be able to almost completely cover the physically interesting parameter space. So even if we don't detect anything from this program, we'll be able to rule out all alternatives to the standard vanilla single field inflation. So I think that this is going to be very exciting, even if we don't detect anything. Of course, if we do detect something, this will be groundbreaking as well. So I think that this is an example of a win-win situation and an application of galaxy survey that will definitely tell us something new about the physics of the early universe. Now let me say a few words about this unknown that I advertised at the beginning of my talk. There is one more interesting observation that was made recently. Now with the 4-point function of galaxies, this was the the detection of the parity violation in the galaxy distribution, which must be, if true, must arise from inflation. So the idea is that so parity is the difference between left-handedness and right-handedness. And with the 4-point function of galaxies, you can calculate this difference. You can test this difference very precisely because the 4-point function is the first statistic that is asymmetric. That is not symmetric with respect to the mirror reflection. So if you have a 3-point function, you can mirror reflect it and almost rotate it back. But with the 4-point function, this doesn't work anymore. If you mirror reflect it, you cannot rotate it back to the original configuration, which means that the same configuration and one configuration and mirror image, they're truly different, and we can go and open the data and check how many quadrilaterals, right-handed quadrilaterals and left-handed quadrilaterals are there. And it was basically detected. So people have seen, well, including again Oliver, who is here in the audience, they have detected this asymmetry, and the significance of this detection ranges from 3 to 7 sigma, depending on how optimistic you are about the errors.
So you want a dash, not a division sign there, right?
Yeah, I would say, yeah, I want a dash. Yeah,
Thank you.
Yeah, thank you. Good point. Right, and a good point about this test is that, so we know that gravity respects parity, right? So galaxy formation physics, G stability cannot generate this signature. So if this parity violation signal is true, then it must be generated by primordial physics. And actually, in a follow-up theory paper that was aimed at explaining the signal, we derived an interesting statement that, so we consider this Eve-Turing inflation. So Eve-Turing inflation allows you to parameterize this parity violation in a model agnostic way. And there is only one operator, well, basically that generates this the parity violation at least in order. And we checked that the observed signal doesn't match the shape of this, the trispectrum predicted by this operator. So in other words, the signal has some scale dependence, and the scale dependence predicted by symmetries of a single field inflation is different from the one that is actually observed in the data. For instance, here you can see that we have a lot of power on these particular scales where the theory template predicts nothing, and the theory template, on the other hand, predicts a lot of power for some other configurations where we don't see any excess of parity violation. So if this discovery continues to be true, if this is true, then I would say that this would rule out single field inflation based on this symmetry considerations. All right, in the dying minutes of my talk, let me say a few words about dark matter. So I'm going to completely change the gears here. Let me just say that, yeah, I started with saying how great cold dark matter is that explains all the data, but actually it's not exactly right. So there are some small scale problems that people are discussing. And so I'm not going to go into details of them. Let me also say that there are some theoretical considerations that suggest that cold dark matter might not be the end of the story. One of them is the coincidence problem, or the let's say numerology problem, that the density, the observed density of dark matter is only 5 times greater than the density of baryons. So it's not 10 to the minus 5, it's not 10 to the 5. And in principle, you can get, this seems to be like, these two sectors seem to be independent in most of the models. Like in CDM, dark matter is completely decoupled from baryons. Why would their densities be similar? So this suggests that the two sectors actually have something to do with each other. And I think that these observations, they motivate, the idea that dark matter might not be exactly cold, or at least its fraction might not be exactly cold. And turns out that large-scale structure is more sensitive to these sort of scenarios than CMB or things like dark matter direct detection experiments. So one example of this situation, one example, of a model we're super sensitive to is given by axions. So axions are basically free scalar fields that can be dark matter, that effectively behave as dark matter, and you can start with their free Klein-Gordon equation in the expanding cosmological background and derive the equation for, let's say, structure formation, this model, and you're going to find usual earlier equation, but supplemented with something that's called an effective quantum pressure. So there's going to be an effective pressure term that basically prevents a structure from being formed on small scales. And if you assume that only fraction of dark matter is made of these axions, then this will result in the observed structure being suppressed as a result of this extra pressure. So the power spectrum in this model with some fraction of axion dark matter is going to be suppressed compared to the power spectrum in the CDM model. And for instance, if you assume that axions contributed to 3% of dark matter and their mass was quite small, let's say 10 to the minus 27 electron volts, you're going to see a suppression of order 30% of the galaxy power spectrum, which is of course much greater than the error bars that we have right now. So we have tested these models for many different axion masses with the data and have found very interesting results. So here in this plot, I'm showing you the allowed, let's say, the constraints on axion dark matter on the abundance of axions with respect to the total abundance of dark matter. So here I'm showing the log of this ratio of its density. So when it's 0, it means that in principle, all of dark matter can be axions. And then here I'm showing you these results for many different axion masses. And basically the first observation here, well, here I'm showing you the results from the galaxy surveys alone, from the CMB plant measurements, and from their combination, here in green. And you can see that for some of the masses, let's say around 10 to the minus 28 electron volts, the addition of the galaxy clustering data improves the CMB only constraints by orders of magnitude. For instance, in this particular case, 10 to minus 28, 10 to minus 28 electron volts. But also there is a regime where the galaxy surveys are more constrained than the CMB by themselves, and also, in combination altogether, when we get the combination of CMB and Planck, we're going to get much better constraints again than Planck alone. Whereas for this particular mass, 10 to the minus 25 electron volts, the large-scale structure, even the current large-scale structure, is much better than the CMB. And of course, in the future, we expect these results to be even more impressive. So this just means that the addition of this galaxy clustering data on top of the CMB allows us to significantly improve, to reduce the allowed parameter space in this plot, where I show the axion masses versus their density. And well, here it's a logarithmic plot, so you can see that this band actually improves things by, let's say, a factor of few. And this is not the only dark matter model that can be tested with galaxy surveys. Another scenario, which I think phenomenologically is similar but physically is very different, is the dark matter baryon interactions. So imagine that there is some momentum exchange between dark matter and baryons, and let's say not all of dark matter, but 10% of dark matter. Then in this case, you're also going to find some extra pressure in the dark matter sector, and this pressure will prevent, structure from, it will suppress structure at a certain scale, and basically you can also introduce this, let's say, 10 or 20% suppression of the power spectrum at small scales. And we actually find that the combination of the current spectroscopic and photometric galaxy surveys and the Planck CMB observations give a preference, a very small preference, which of course quite insignificant at the moment, but in principle, well, we see that the data is better fit if you allow for some small cross section, for some small momentum transfer cross section between the baryons and dark matter. And this is just an example that, well, we're not saying that we have detected this. We're just saying that we're sensitive to this scenario, and it will be interesting to investigate this in the future. So I guess that, yeah, the very last slide that I would like to show here is the following. So I presented all these, measurements coming from the EFT applied to calculate, 2-point function, 3-point function, and compare it with the data. But it's not clear if this is the best that we can do in principle. And there are many other techniques like field level calculation, simulation-based inference, voids, counts and cells, and so forth, so on and so forth, that basically are based on the idea that the observed galaxy distribution is not equal to the sum of the summary statistics, such as the power spectrum by spectrum and so on. And in principle, it could be that we're losing a lot of information, and it would be nice to really understand this question. And the best way to do it is to, again, run a data challenge and to confront all these different techniques with the realistic data sets. And this is precisely the goal of a workshop that takes place in the University of Arizona now, and it's organized by Elizabeth here. University of Arizona Beyond 2-Point Function Data Challenge is going to tell us what techniques are the most informative and which one of them will be leading our progress in cosmology in the future. So and the future is about to come, and we expect, all the results improve by a significant number, let's say factor 5 or 10 in the coming 5 to 10 years. And let me conclude by saying that I hope I have convinced you that perturbative techniques are robust and can be applied to analyze data from large-scale structure, and that we can, by doing so, we can obtain cosmological parameter measurements competitive with other probes such as the CMB, and in principle obtain new ways of test fundamental physics, such as the parity violation in the initial conditions, and so on and so forth. And we expect huge improvements in the future, and we hope that with these improvements, many order 1 questions about the nature of dark matter and inflation will be answered. So thank you very much for your attention.
Thank you for this grand tour of physics. Questions?
Yes, I have 2 questions. One on your primordial non-Gaussianity and the other on parity non-conservation. So I'm guessing the primordial non-Gaussianity signatures in the large scale structure would be more prominent at smaller wavelengths. Is that right?
It depends. It really depends on the type of non-Gaussianity you're looking for. For instance, for the single field, for this local type of non-Gaussianity, it's really important to have like a generous coupling between small scales and large scales. So it's really important to have a large range of scales to test this model. But for instance, for other type of non-Gaussianity, the one generated by, let's say this type of operator, it's important to look at wavelengths at fluctuations with the same wavelengths. Basically, you're correlating three density fields, three modes. Well, basically, three density fields with the modes which are similar, and that's why this type of non-Gaussianity is called equilateral. So each wavelength, from each density field is the same. So it really depends on the type of non-Gaussianity.
So how much does the impact of baryonic unknown or like baryonic physics matter in this?
Well, I guess, yeah, the answer to this question is the following. So we know how to incorporate baryons by using these perturbative techniques, and we marginalize over this, nuisance parameters. Now the question, how much do we lose by marginalizing? It seems that we lose quite a bit. We lose very significant information. So basically, if we could understand the baryonic feedback better and predict this nuisance parameter or extract it, let's say, from simulations, then our constraints are going to improve even further. So I think that eventually, for this type of non-Gaussianity single field, it's knowledge of the baryonic feedback and these other nuisance parameters that will be fundamentally limiting our constraints.
And about the parity violation, so you require 4-point correlation functions, and
Yes.
I am guessing in order to get reliable 4PFs, you need a lot of galaxies. So
Yeah.
I'm just worried whether this could just be a manifestation of small number statistics, and I'm wondering if we have checked it on n-body simulations that are motivated by purely parity conserving initial conditions, and whether in small boxes of such simulations can you potentially see signatures of parity violation which might be non-physical.
Well, here, I think it would be fair to say that this phenomena was understood only recently, and there were very few tests. So the one thing that we have done is, of course, we checked it with current data that we have from BOSS. Basically, we have a sample of 2 million galaxies, and I think this is already enough to, this measurement was done on them. So this was enough, for instance, to build this kind of scale-dependent statistics. So in principle, yeah, it's a great question. How does it scale with, let's say, number of galaxies and the volume? I think that our expectation that the volume is going to be more important for this particular probe. Is like how many, basically, is not the number of galaxies per se, but how many different quadrilaterals are you going to have in your survey? So it's both the question of, the number of galaxies, but also the volume that you're covering.
What?
Yeah, I've got some questions maybe related to the first of the questions you just asked. So maybe a little bit tangled together, but you started off by talking of information simply as linear, the number of modes. And, I might ask the question, where do you need the modes to really get this stuff? I mean, ultimately, the position of the people in this room probably doesn't have information about cosmology. And so related to this, with your impressive treatment, I can't tell if it's interesting because it's doing better on larger scales where we have things like DESI, or, if you're really reaching down to galaxy scales and you are really mining information that hasn't been touched there before. I mean, where's your signal actually coming from that you care about?
Yeah, thank you. That's a great question. So this technique that I introduced, it applies only, large scales, right? So
What's large scale concrete?
100 megaparsec, like greater than, let's say, 5 megaparsecs. Now, as part of this workshop, we want to understand what is the amount of information that is actually there in small scales. This question is still not clear, right? Because some people claim that there is a lot of information on small scale, but there is nothing once you marginalize over all the astrophysics uncertainties. And I think that this is something we would like to understand. So, of course, we can analyze, with things like this. Okay, we can go to large scales, we throw away, this small scale data, we can describe it, fine, we get our constraints. Are we going to lose a lot or not? So I don't know yet the answer, but we're going to, hopefully, thanks to the workshop we're organizing, we're going to know the answer.
Nick?
Yeah, so for these sorts of parity violating EFT interactions, Are they just not observable in like the CMB, for example, because you really need 3D information to actually be able to get at them? Or can they be tied to the like non-zero EB cross correlations that have been measured in the CMB recently by Komatsu and company?
Yeah, that's a very good question. So I think it's two actually questions. Okay, the first part is the following. Yeah, can we constrain these things with the CMB? Yes, but it's a bit subtle because in the with the 2D plane, so if you assume plane parallel approximation, 2D everything, you lose this effect that 4-point function on the plane, you can mirror reflect and rotate back, no problem. So you lose this effect. But then you will have some extra information through things like the finite thickness of the scattering surface, or some relativistic effects that go beyond the not relativistic, well, the effects beyond the plane parallel approximation. So you'll be able to extract some information, but the scales are going to be different from this. Now, in regard to the ENP measurements, I think that it's a different probe. It's also kind of different type of parity, but here specifically parity in the initial kind of like parity in the statistical sense, right? In the statistical distribution, we calculate the 4-point function, which is different from what people mean when they compute this EB correlation, which is more like the parity in the sense that chiral molecules, right? The rotation of the polarization plane. It's a different phenomenon that has nothing to do with the statistical parity violation. So these two things I would say are unrelated. Even though in some models, of inflation principle, you could have some, let's say, axial inflation with, f of dual. You can in principle try to generate both. Like physically they can be related, but not the way how we measure them.
So gravity can give you this type of parity violating things. Like, is there anything observationally systematic-y thing that would give something like this, or is this really just like primordial or bust?
Yeah, that's a very good question, because I think that what is most important for this kind of measurements right now is our understanding of the covariance matrix for this problem, because we do find some kind of that the data looks very different from, let's say, the distribution that we obtained from the MOCs, right? But the MOC catalogs, they were generated based on the observations of the power spectrum, right? They're recycling the 2-point function information. It could be that their 4-point function is actually completely wrong, and this test therefore underestimates the error bars. So at this point, I would say that the crucial thing is the error estimation. Is not. I mean, there could be other, I guess, systematic effects, but the most important one is the one of just reliably estimating the spread of the distribution here. So this is the key. This is the key systematic bottleneck right now.
Okay. Thank you again, Misha.